Average rate of change. Before we jump into how to calculate average rate of change mathematically, let's first discuss what is necessary to describe change in general. To describe change, you need 2 points of reference. So for example, let's say I show you a picture of a person you've never seen before, and I ask you to describe how this person has changed. Your follow-up question should be, from when? Do you want me to describe change from the day before, from the week before, from a year before, from 10 years before? The point is, in order to successfully describe change in a specific manner to that individual, you need a second point of reference. And the same thing is going to be true when we calculate a rate of change in mathematics. So we're going to need 2 points. Now our reference points in math are going to be x, y coordinates that are on the function given in that problem. We're going to call those points for now x1, y1, and x2, y2. Now, what exactly are we doing when we're calculating average rate of change? Well, let's draw a function that has curvature. So what you've been doing up to this point when you're calculating rate of change, which should be a familiar term to you, is you've just been finding the slope between 2 points of linear functions. And linear functions, because they are straight, have a constant rate of change, meaning that the rates of change are always the same no matter what 2 points you're calculating the rate of change between, or what 2 points you're calculating the slope between. But when we look at a function that has curvature, which will appear often in our course, is that the rates of change are not constant on these functions. If I designate these 2 points that we want to find the rate of change between, those 2 red points, we can see as we move from one point to another. So if I start at the leftmost point, we can see that the rate of change is negative when we start. It's going down. That function is decreasing. Then it bottoms out, so it's going to have no rate of change. It stays in one position, and then it changes to an increasing function for the rest of the time, so it's going to have a positive rate of change there. So the point is that the rate of change is not constant when we have curvature in our functions. And therefore, the best we can do at this point is just calculate how the function is changing on average between those 2 points. And in order to do that, all we have to do is calculate the slope of the line that connects the 2 points that we're looking at in the problem. Okay, this line is referred to as the secant line. So when finding average rate of change between 2 points on a function, what you are doing is calculating the slope of the secant line. So we know how to calculate slope. We know slope, which is often designated by the letter m, is our change in y over change in x. And we know that required 2 points. We know change in y is just the difference between the y values, and change in x is the difference between the x values. So this is our traditional slope formula that we use with linear functions. And we're going to use this same formula, but we're just going to change some notation to get used to function notation more often. So instead of that m, I'm just going to write average rate of change. And it's going to equal, we said before that y is the same thing as f of x. So instead of y2, I'm going to write f of x2. And instead of y1, I'm going to write f of x1. They mean the same thing. So I'm just going to make those replacements so that we have this as our average rate of change formula. This is just the slope formula using function notation. And as a reminder, what this function notation is telling us to do is we want to find the y value at x2 for this first one, and we want to find the y value for x1 in the second one and substitute it into our average rate of change formula. Once we make that computation, simplify that, we'll find the average rate of change. And again, that represents the slope of the secant line, and the secant line is the line that connects the 2 points that we want to calculate the average rate of change between. So having said all that, if you want to mark something down, this is the formula we're going to be using. Let's jump over to an example. I have a function here on the screen. This function is named g of t. Its input variable is t. We can see it's on our x-axis, which is our input axis. So let's pick any 2 points to start. We'll do maybe 2 of them. Let's say I choose this point to start, and I want to find the average rate of change between that point and this point here. So we now know that average rate of change is calculating the slope of the line that connects those 2 points. So if you want to draw on a line, that can be helpful in some cases. And again, the best we can do is find on average how is this function changing from that first green point to that second green point, because we notice if we were to trace along the function, the rates of change are not constant. They're changing all the time. This thing's increasing at different rates to begin with, and then it reaches a peak, a maximum point, and then it starts to decrease, and it's not decreasing at the same rate, right? It's kind of flat, and then all of a sudden it gets really steep. So that's an indication that we don't have a constant rate of change there. So again, the best we can do is find the average rate of change between those 2 points. So let's make that calculation. We're going to say the average rate of change we know is equal to f of x2 minus f of x1 over x2 minus x1. So this formula requires 2 points. So what are our 2 points? We can mark these down right on the graph if we'd like. This first point is -3, -2. And this second point is 2, 0. And if you even want to make a note underneath that your -3 is your x1, your 2 is your x2, your -2 is f of x1, and your 0 is your f of x2. So remember, f of x1 and f of x2 are the y values at that x value. So now let's plug it into the formula. So f of x2 is 0 minus f of x1 is -2 over x2, which is 2, minus x1, -3. So we're going to get 0 plus 2, which is 2, and we're going to get 2 plus 3, which is 5. So the average rate of change between those 2 points is 2/5. And since you know that the average rate of change is just the slope of that secant line, if you're used to rise over run, you can use that to check your answer. To go from that first green point to the second, moving left to right, we rise 2 and we run 5. So that's a good way to check. And we also see that our blue line is increasing, which is indicative of a positive rate of change. So the fact that we got a positive slope answer is also a good sign. So there's an average rate of change problem with a function graph. Let's do one more, but between 2 different points. Let's use this point here and this point here. So that point is -1, 1, and this point is 3, -2. So you can designate either one to be your x1 and your x2. It doesn't matter whether you want the 3 to be x1 or the -1 to be x1. It doesn't matter as long as you stay consistent with the corresponding y value to that point being the f of x1 and the f of x2 respectively. So let's call -1 x1 and 3 x2. So we're going to do 3 minus -1. So our f of x2 is going to be -2 minus our f of x1 or x2, x1, yes, it's going to be 1. So -2 minus 1 is -3. 3 plus 1 is going to be 4. -3/4 is the average rate of change between those 2 points for this function. And again, that is the slope of the line that connects those 2 points. And we can see if we wanted to calculate the slope of that green line, down 3, right 4, for a slope of -3/4. That green line is a decreasing linear function, so I expect a negative rate of change or a negative slope. I did get that in my calculation, so we should feel good about that. So that is how you calculate average rate of change using a graph. Now, how do we calculate the average rate of change if I'm just given a function equation? So let's say I have f of x equals x squared plus 2, and they tell me to calculate the average rate of change over the interval of -3 to 5. Now, when you see this, that is an interval, that's not a coordinate. So over the interval along, this is important, the x-axis. Okay, so this is telling you to calculate the average rate of change over an interval that runs along the x-axis. That's what it always tells you if it gives you an interval. So it's never along the y-axis, which means we can mark off our x coordinates right now. We can say that this -3 is going to serve as our x1, and this is going to serve as our x2. So we're finding the average rate of change along that interval. We do not need to graph this function in order to calculate the average rate of change. We know that we need to compute slope, and we know that we need two coordinates. We have the x coordinates for each one. How are we going to get the y coordinates? What we're going to do is we're going to plug in these x values, because we know that the y coordinate represents the output of our function given a certain input x. So what we're going to do is evaluate our functions at those given x values. So we're going to evaluate the first one at -3 and the second one at 5. So f of x, remember, that's our input variable. So this time I'm evaluating the function f at -3, and all that means is I'm going to replace the x, or plug in -3 to that x. So it's going to be -3 squared plus 2. Make sure when you plug it in, you're plugging it in parentheses so that you know to square -3 and not square 3 and then multiply it by -1. So a successful order of operations is needed to get this question right. So -3 squared is 9 plus 2 is 11. F of 5 is going to be 5 squared plus 2. 25 plus 2 is 27. These numbers that serve as the output are going to be our y value. So let's mark those down as, if -3 was our x1, let's make sure we're careful and staying consistent. This is our y1, and this is our y2. Or you could think of it as your f of x1 and your f of x2. Now we can go to our average rate of change formula, and we're going to do f of x2, which is 27, minus f of x1, which is 11, over x2 minus x1. And we're going to get 16 over 8, which is 2. So the average rate of change along that given interval for this particular function is equal to 2, or the slope of the secant line that would connect the points -3, 11 and 5, 27. The slope between those 2 points would be +2. So that's an example of how to calculate average rate of change when you're given a function equation and an interval over which to calculate the rate of change between.